they have a voltage source like so. All right. Now, class, I want you to pay attention to this one. This one showcases so many things that you'll need to know. First, you'll notice the values here of the inductance and capacitance are given, not the reactances. You see no J there. Does everybody follow me on this? Very important that you're not afraid or misunderstand something. Next thing you need to do is take this, and we need some basic information. Now, I want you to just take a look at that. It's 526 if you want to know which one it is. Now, I hope you can see this. If by looking over there, you'll notice that the actual voltage is giving in the time domain. That is observable. In other words, you can measure it, you can see it. Whenever you're giving a voltage like 30 at an angle of, or 30 volts at an angle of 30 degrees, that's in the phasor or the frequency domain. You can't measure that per se. Y'all with me, class? Very important. That's observable. Now we need some parameters. First, by looking at this, what is the frequency in omega? Take a look. How many see it's 377? Just raise your hands. Can you all read it? That's critical. So I know omega here is 377, and that would be radians per second. The thing I do not like about this is he has radians per second times t, which would be seconds. That's radians, and it's added to degrees, which drives me bananas sometimes. I always tell my students never to do this. He's the author of the book. He says, I'm doing it this way, so he gets away with it. But you normally never mix units like that. Y'all follow me? Degrees are not radians. Radians are not degrees. You can't add them together without adjusting one of them. Y'all with me, class? Very important you hear me. Now, what I'm going to do is forgive him for that. And I'm going to take this and take this circuit and put everything into the frequency domain like we did on Wednesday. Everybody with me? So first thing is this voltage. And he loves 12 times square root of 2 because we're going to find out later we're going to deal with something called an RMS voltage. But don't worry about that. It just means the square root of 2 will disappear. We're not doing it now. Anyway, do you all see the magnitude of this voltage? This 12 square root of 2. I hope you can see it in the far back. Y'all with me? Can you really see it back there? You just, I think you're razzing me. There's no way you can see it back there. There's no way. I mean, an eagle would have a tough time reading it. All right, but I'll give you, if you want to sit back there, have at it. So now I go ahead and I put down, now pay attention to this. This voltage has the magnitude of 12 square root of 2, but the angle, see, it's always going to have a cosine form. If it has sine, we'd have to do something. We'd have to adjust it by 90 degrees, but don't worry about that. We're not going to fool you. That angle comes over here. So this is going to be at an angle of 90 degrees volts. Now that's in the frequency or phasor domain. Y'all with me? Now the next thing we do, we have to take these elements and make sure instead of values of L and C, they're ohms. Y'all with me? This one's easy. That's just 4 ohms. And this is the voltage, by the way. This would be source voltage. Now, next we have a resistance of 4 ohms, right? Just leave it as 4 ohms. Nothing better than that. It's 4 ohms in the frequency or time domain. Next, what do we do with this inductance? The inductance is 15.92 millihenries. And do you remember the actual value of the impedance of an inductor? If you had an inductor here of a value L and you wanted the impedance, the complex resistance, it would be what? J omega L, right? How many remember that? You'll need to know this very well. It can't even be something you wonder about. This has to be an automatic, like 2 plus 2 is 4 kind of thing. So what would the impedance of that be? 15.92 times 377. That 377 is 120 pi. I'm just going to tell you what it is. Just take 120 pi times 15.92 times 10 to the minus third, and that would be the impedance, and there would be a J. What is that value? Please. Anyway. Who asked this? Get a calculator. What do you got? You got a calculator? 15.92 times 377. 6? Anybody confirm that? That's 6. 6 to me. Now, what about the capacitive reactance? What is this capacitive reactance? You'll need to know these things. If you got C, the reactance, or the impedance, capacitive impedance is what? Minus J over omega C, or 1 over J omega C. Y'all with me? Show of hands if you understand me. I'm trying to speak loud and clearly so you can get this. In the far back over there, if you guys can see it, power to you, more power to you. All right, now what is this value? I need help. What is it? Minus, all right, minus J2. All right. He wants what in this problem? He wants a bunch of voltages, right? Here and here and here. You want a bunch of voltages? Yes, sir.
You rewrite the capacitor.
This capacitor has a value of 30. I'm sorry? Right here? All right, a capacitor. I'm trying to get a pen that is not dead. And these, by the way, I just pulled these markers right out of the cabinet. They're supposed to be fresh. And if they're fresh, then we're in bad trouble. Nothing that works around. All right, here, listen. I think you'll see this. The value of the impedance of the capacitor is equal to minus J over omega C. Can you read it? You okay? Yes, sir.
For my value of the impedance for the capacitor, I got this 1.
Anybody else? All right, take omega, which is 1326 times 10 to the minus 6, times, take 377, pardon me, times 1326 times 10 to the minus 6 and 1 over. And just tell me, do you get minus J2 or not? What? Say, I couldn't hear you, sir. Yeah. Can you read this at all?
Is it 1326 or 132.6?
I think it's 1326 micro, right?
What's 13? Oh, okay.
Couldn't read it?
I thought it was 132.6.
No. It's 1326, right? Right. What do you get? Is it going to be minus J2?
Let's do it.
All right, so we're going with that. Everybody, can you all see it? All right, you got that. Now we're in this domain called a phasor domain. All right. Now you'll notice if we want the and they want the voltage here. They want the voltage here, and they want the voltage here, right? The only thing you need is the current, because the current times those impedances will give you the voltage. You all with me? How many understand that? How do you get the current? Doesn't matter if they're complex resistances or not. If you want this current, we're in the phasor ring. If I want this current I, you'll notice we have one loop equation, one single loop. Everybody? So the total voltage that would be driving that current is simply this voltage. I'll put it there in a second. It's 12 square root of 2 at 90 degrees. And what's limiting the current are all these impedances. Now, I'll get to the reduction in a second, but how many understand the thoughts? All right? How about if I do it right here? I hope you can see this. So to get this current, now this will be a phasor current. I don't care how you do it. It's going to have a magnitude and angle. You all with me? Get your calculators out. Make sure you can do this stuff. There's always somebody fouls it up and says, but I knew what I was doing. No, you didn't. If you didn't get the right answer, you didn't know what you did. Try to tell that to a football coach. But I had the ball. No. Fumbled the ball. God, I wouldn't want to be in our locker room. Anyway, so the voltage is this. Now you can put that in any way you want, but guess what? You can also put J 12 times square root of 2, because that's what an angle of 90 degrees means. It just means J. Y'all with me, class? Or you can put, that polar form would be 12 square root of 2 at 90. So this is going to be J 12 square root of 2. The J is the same thing as 90, one at an angle of 90 degrees. You all hear me on this? Now you divide it by everything. Now, obviously, we got 4 ohms, right? That's the first thing, but what about the second thing? This is one thing I try to tell. I'll just put 4 here. What about this? What can we do with these two? And it results in J what? 4, right? J6 minus J2 is J4. How many see that? Good. So I got 4 minus J4. Now I'm going to tell you this right now. That would be the current. And this board has seen better days in terms of its markability and stuff. The markers aren't there. Now look at this. I'll just tell you, do this on your calculators, tell me what you get, because this is probably what you're going to do. But here's what I phasor is. Well, I got J12 square root of 2. I'm going to put this as 12 square root of 2. I'm going to leave it at an angle of 90 degrees for a reason. Because I look down here and I see 4. Yes, sir. Yes, yes. That was my oversight. I'm sorry. Thank you very much. Now just listen. I see 4 plus J4. 4J4. It's a right triangle kind of deal. The hypotenuse or magnitude is square root of 2 times 4. How many see that? Right? So this right here can be rendered as simply 4 square root of 2. Maybe that's why I put the square root of 2 in. And the angle here would be 45 degrees. Can everybody see that? Can you follow me in the far back? Can you really see it back there? Not the very back row in group. Can you really see that? Yeah.
I don't understand what you just did.
Can you read this first of all? Wait, just let me help. Can you read that? All right, so if you have a real part of 4 and an imaginary part, J4. You see how the hypotenuse here, this would be 90 degrees, that'd be 45. Can you see it? All right, that's a right triangle, right? This squared plus this squared square root is this, right? Square root of that. So it's really 2 square root of 4, right? So that's 4 square root of 2 right there. Can you see that, sir? You got it? Your calculators will do this. You don't have to think deep about it. Just make sure you know how to use them. Now, the only reason I did this is why? Well, that means my I phasor here is what? Well, I got 12 divided by 4 is 3. The square roots of 2 kill each other, right? You all see this? I mean, I'm just asking because I want to make sure you can read my writing, but it's bad enough. Then I have 90, but when I take 45 from the denominator to the numerator, it's minus 45. So I'm left with simply 45 degrees. You all see this, class? How many do? Now, if you wanted to put the current in terms of the time domain, if that was asked for, I'm just going to complete this idea. All right. So if I wanted that current in terms of the time domain, I want to put it here, and I want to make sure you see it. These markers, this board, everything is not doing too well. Hear me now. That's what I got here. I have a simply what? Where did I put it? Did I erase it? All right. I have I phasor equal to 3 at an angle of 45 degrees amps. I hope you can read that. I'm trying my best. This thing is, no matter what I do, I seem to get a rotten marker. And I thought I put a good one here. Unless somebody walked off with it. Oh, this one. Thank God. All right. So it's 3 at an angle of 45 degrees amps. Now in the time domain, I of t will have that magnitude, 3. Y'all hear me? Then it will be the cosine of omega t. Omega is 377 for this one. I can put down omega, I'm just put it as omega t so you get the idea. That is something you have to observe from the actual voltage waveform that's causing this. You all with me? 377 for us. Everybody got that? T. Now the angle is 45 degrees. So you would add 45 degrees here and that would be amps. That would be in the time domain. Y'all with me? Now I don't like 45 degrees. My kids did that in my radar class or something. They'd hear about it. They might lose some points. But in this book, it's acceptable. Technically, that's pi over 4 radians. Y'all hear me, class? How many know pi over 4 radians is 45 degrees? Hopefully everybody here. All right, it's something, and by the way, in ME, I'm sure they yell at you about this too. In every major I know of, they always make sure you don't mix units. Because if you do that, things start blowing up. You don't do that. All right, that would be in the time domain. I don't think they even asked that. But we want the voltage, and I think he wants, does he want the phasor domain for this problem? We can get them in both. Let's get phasor, because that's the only one that really matters for this stuff. And I'm going to level with you. I'm going to ask for the voltage and currents in the phasor domain, specifically for magnitude and angle. Y'all hear me? I hope you hear. And I hope this goes out and they listen to it if they're not here, because we're missing a bunch. All right, now, let's get this voltage. First, do we know the current?
Yes.
What would this voltage be? Just R times I, right? So I put it here, V of R is equal to R times I. R is 4. The actual current is what? 3 at 45, so it'd be times 3 at an angle of 45 degrees. Or it's 12 at an angle of 45 degrees volts. Now take a moment and just let me know, how many see that? That's all it is. Current going into the positive terminal times the impedance of the resistor, which is just 4 ohms. Got it? There's nothing mysterious here. All right. That was mysterious. Anyway, what is this voltage going to be, VL? Plus to minus? Well, it's the current going in 4 at an angle of 45 degrees, right?
3.
Or 3? 3 at an angle of 45 degrees. What? Times what? J6, right? Take your calculator, see what comes up. J6 ohms. Now, how many know that J6 ohms is 6 at an angle of 90 degrees? Isn't that right? Why don't put it that way? You know, save yourself some time. So I can say the voltage right here across this, I'm trying to be careful, but would be equal to 3 at an angle of 45 degrees. And then it's going to be times 6 at an angle of 90 degrees. Now, the only thing you do is multiply the 6 and 3, get 18. I'll get out of the way. And the angle for that one is you add the 45 and 90, or 135. How many can see that? Far back there, guys. All right. So that's 135. Okay? What about down here for this capacitor? You'll notice the sign, plus to minus. So you want the current, phasor current, entering the positive terminal. Y'all follow me? And then we multiply it by the impedance, which happens to be minus J2. Y'all with me, class? Take a moment. Make sure you capture everything I'm saying. So that voltage, this VC, would be the current 3 at an angle of 45 degrees. And technically it's just times minus J2. Right? I'll get out of the way. I'm going to mention something. I'm not trying to shout at you people. Right? So it's going to be 3 times 2 is 6, right? Then I have an angle of 45 degrees here. What is minus J? 1 at an angle of, well, yeah, but minus 90. How's that? All right? I mean, I like the smaller value. You're right. Whoever said. So it's really going to be this minus 90 degrees, and you can see that this is going to be equal to 6 at an angle of minus 45 degrees. You're absolutely right with what you said. How many see this? Could you please take your calculators out and make sure if you get this kind of a, that's a polar, 3 at an angle 45, that you can multiply it by minus J2. And I want it in terms of a magnitude and angle. Just please do it now. I'm really concerned about this because there's so many people who are very careless and casual. And then they fail a quiz because they don't know how to use their calculators. Yes, sir?
Do we have to solve the polars that way? Or
Say again?
do we have to solve it with like the angle of the polar?
So I'm going to ask for the polar. It's magnitude and angle. I want the angle in degrees.
So but if we solved it all the way through using like J,
That's fine. You can. It's called rectangular. Real and imaginary is rectangular. You can, but the final answer I'm asking for is in polar. So I think all your calculators can take it's called a rectangular, a real and imaginary, and turn it into a magnitude and angle. I'm almost positive. Isn't that right? How many can confirm that? If you haven't done it on your calculators, do it now. You don't know how much you're hurting yourself not doing this and having confidence in what you do. Yes, sir.
Could you do also negative 6 to the angle of 135? Would that be the same answer?
Hold on. Which one?
Just like down there.
Like here?
Yes, since it's negative J.
Let me ask. I want to answer this question. Please listen. Now, if you have any number, I'm answering it in a way that I think is going to be more complete. If you have A at or minus A at an angle theta, it doesn't matter what A is. Y'all hear me? That is identical to A, magnitude of A, at an angle of whatever it was before, plus or minus 180 degrees. You can add or subtract 180 degrees from that angle, and you will get, as a fact, I think you're right, right? Y'all hear? I mean, does everybody understand what I'm saying? There are many different ways to render the same exact value. You can have -1 at 0 degrees, or 1 at -180, or 1 at +180. They're all the same points on the complex plane. Follow me, class? All right? All right, now the reason I'm asking for it in polar, because if you have it in polar, you can easily go to the time domain. The magnitude just shifts over. Then you got that cosine of omega t, and you add the angle. And you're back in the time domain, the observable domain. So that's the reason I do this. And by the way, a lot of times, people almost have a natural animosity to doing that. Don't. It's just the observable domain is the time domain. That's the thing. If we measure stuff, we can measure in the time domain. It's the way it is. Okay. You have it. By the way, it's an excellent problem. Who asked this one? Someone. Who? The guy who's talking? Right there? All right, good. It isn't. I'm used to this. Especially when I'm teaching. Some of the courses right before they got an exam in the next class. The last thing they want to do is hear me say something that they're not getting tested on. You have an exam or something? You couldn't have an exam. Do you have one coming up right now?
We have a 32 exam.
What?
32.
Today?
Yes.
Oh, that was sweet of them.
Yes.
Right after a major storm, what could be more obvious? Of course we give an exam. Go ahead. I'm kidding. Don't get me in trouble for that one.
No.
Is this Birch?
No. Williams?
I don't know. Birch would probably come over and sink my boat. Go ahead.
How close do you want to angle I plugged mine into my calculator, I got like 134.998.
What did you say? One
Never
point.
mind, it doesn't actually
I
matter.
believe me, rounding errors in the third decimal point, I could care less about. I don't care about it. This is not a precision measurements course. Then I would. I pick these atomic physicists guys. They do stuff that drives me insane if they measure. They need 38 places after the decimal. No mind. Go ahead. Hold on. Let's speak up. I'm sorry.
How do you get from the original expression voltage to voltage phasor?
How do I?
Going from the original expression voltage to the voltage phasor.
All right, he's asking how do you go from time to phasor? I think I'm just paraphrasing. Is that it? All right, here, guys, just listen. Anytime, and can you see it right here? If you have a value, doesn't matter what it is, V naught, just call it V naught. It will be, if it's in the time domain, a cosine value. Cosine of omega t. Omega is found by looking at the coefficient of time. That's it. Plus an angle. It should be in radians, but it's not in this book. To take that and go to the phasor domain, the magnitude V naught comes over. Maybe I should do it this way. So you bring V naught. You eliminate the cosine of omega t. It's gone. The only thing you do is take that angle and put it right here. That's it. Now, the thing you have to get from this is the value of omega, because that value of omega is used to get the reactance here, or impedance. It would be J omega L, or the reactance here, or impedance, which is minus J over omega C. Do y'all follow me? How many understand that? I'm trying to be really, really clear so there's no misunderstanding. There's always these people that have kind of listened, but they have things to do, and then they miss the subtle points that are so important. All right? Now, in fairness, I'm not going to ask you to go to the time domain this time, but there will be a point where I will. Just understand it. Y'all with me, class? I prefer to do another problem. They're all the same class. You realize that we're just applying what you learned. This is Kirchhoff's current law and Kirchhoff's voltage law to single loop equations, right? Let's do one. I mean, if you got, does anybody have another one? By the way, it's a great problem. I mean that. And I didn't plant that question, I'm glad you asked it. All right. I want to do problem 5.23, okay? And let me erase that board. I'm really going to try, I'm going to try to get it clean. No matter what I do, these markers and this board just do not seem to work together very well.
Yeah, the bottom of the Yep. So you have to match it, SLP.
The best? No. I don't have time to do all, but I just, So I just pick the one that has a Wi-Fi, what
I want to make sure you watch this one. I would watch this one if I were you.
Well, I'm just like, this is what I got last.
There's a lot of things you have to take care of.
The units are all owned, so I'm just going to omit them for now. What they want is this. You can confirm that, but that's essentially what they want, isn't it, class? If you have the access to that. All right, now how are you going to do that? Take a moment. Don't answer anybody. Just think. What looks like maybe it will work? Well, there's probably a lot of things, right? How many see that this side right here is in parallel with this side? Show of hands. Yeah. Two parallel things. What's going in between them? A current of I. Do you think current division would work? Give me a show of hands. It will work. What I would suggest before you just start brute forcing it, take a good look and see what you can simplify. Now, some of you see it right away. In the back, I don't know how you see anything, but I'll take your word for it. You can see it. Still have my doubts. Y'all with me, class? What might we simplify if we were so inclined? Let's start with this side. Anyone? Yeah, all right. I got J2 minus J1 sounds like J1. Y'all with me? How many see that? Can you all see it here or not? I mean, are you good with that? Did you hear me? No, kind of. What I'm really saying is, if you look here, these are all in series, right? I got J2 minus J1. That's J1. And I got one. So I'm going to take that, if you don't mind, and just replace it by J1. All right? All right, let's go over here. Anything look like we might? Minus J2 and J1 is minus J1, right? That would be a I'm going to get rid of the inductor. I like my life easy. And this becomes minus J1, right? Now, how many see this? What am I going to do next? I got the current that's going into both parallel terms of it, right? Both parallel parts. So what would I do? To find the current I1, that would be the current going into both, which is 4 at an angle of 0 degrees. You don't need the 0 degrees. You all with me? Now what do I multiply it by? If I want the current here, I would multiply it by the opposite impedance, right? How many understand that? Okay, opposite impedance is going to be 1 plus J1 over the sum of that plus that. What is the sum of that plus that? Kind of nice. Minus J1 plus J1 goes to 0, right? And I got 1 and 1 is 2. So I really have what? 2 times 1 plus J1. Or you can render this if you want in polar as 2 square root of 2 at an angle of 45 degrees amps. Now just take a look and make sure there's nothing that confuses you. Y'all with me on this class? All right? Hear me. What if I wanted the voltage here? What would that be? Now, I asked this on purpose. This is a two-part step. Let me ask the obvious question. What would the current be going here? There's several ways to get it. I'll call this I2 for lack of a better term. Now look, you got I1, right? You all agree with that? Doesn't 4 amps equal I1 plus I2? How many see that? Why don't we just say, instead of doing current division again, which we could, just say that I2 is 4 minus I1, and I'll just put minus I1 so you can see. Y'all agree with that? Let me see that. These are questions that I kind of ask, and I assume you can see this. All right, now if I have that current, what would that be? Well, it's 4 minus 2 square root of 2 at 45 degrees. You can do it on your calculators. Do you agree with this class? So if I had this current, what would this voltage be? 1 times that, which is that current, right, in magnitude. It's a nice, easy problem if you know what you're doing. Everybody with me on this? By the way, could somebody tell me what this is? 4 minus that, 2 square root of 2 at 45. Give it to me in terms of magnitude and angle, please. I mean, you can use current division to do it if you want. You don't have to do this.
It would be 2 square root of 2 that equals 45.
Who's saying that? Who? Raise your hand. I just want. Okay, 2 square root of 2 at minus 45? Probably. Oops. Now, one thing for sure, if you add I2 and I1, you better get 4. If you don't, you got a problem. You all with me, class? All right, and I think I made my point here, but I'm trying to make sure you see there's nothing really tricky if you understand stuff. It's terribly confusing if you haven't done anything and try to cram it. But I'm trying to make sure I lay this out clearly. Now that's current division and simple voltage division problems. Now we can keep going on. I want to do one more problem that would sort of showcase how the only thing we're doing now is taking everything we learned with nodal, Thevenin, mesh analysis, and applying it to systems that have a complex impedance. This is it. Y'all with me? Yes, sir. Yes, sir. Sorry. I can't think sometimes.
How did you get 2 square root of 2, like, as the, from 4 minus I1?
Well, you want to know the truth. If you look at this, I have 4. Let me just draw it so you can see. This is the real axis, and this is the imaginary, right? So 4 would be 4 units on the real axis. I'm trying to draw this pictorially. Y'all with me? Now I'm subtracting this, right? What is that really? Can't I add? If I'm talking about what is it going to look like if I'm subtracting, well, what does 2 square root of 2 at minus 45 look like? Now I'm going to subtract it. Isn't 2 square root of 2 at minus 45 something that would have 2 square root of 2 here at 45 degrees? That would be minus 45 degrees, right? But I'm subtracting, so the tip of that thing comes up here, and it looks like this. And this would be 45 degrees. How many see that? You remember how to do vector addition. Who said that? Somebody gave me the answer. You gave me the answer, right? Is that what you did? All right, well, what that is tip to tail, right? So you take this vector and you put it right here. Y'all remember this? Come on, man, right? You're looking at me like this is abstract. It's not, it's just vector addition. I mean, if you take 2 vectors, a plus b or a minus b, if it's a minus b, what? You take a, then you take vector b, and what do you do with it? You simply reverse the direction, right? Take that, put it at the tip of vector a, and the remaining hypotenuse, or the point between the two, from here to here is what you get. Isn't that right, class? Isn't that 2 square root of 2? That's what you did, isn't it? I mean, you're calculating. Correct, class? Y'all had geometry. Remember doing this stuff? How many remember doing this? You don't have to do it that way. You're calculating. You got a calculator? Right? Just do it on your calculator. Which kind do you have?
Yeah,
Sydney? Does anybody have an 84 here and know how to do this? Show it, please. Just turn around and show it. I mean, honestly, it's the best way. If somebody knows, they can show you. I don't know how to do it on your calculator. I'm trying to give you the visual on this. You all with me on this one? It's not hard. Okay, that's how I got it, that way. I mean, if you really want to think about it, if you had this plus that, you have to get what? 4, don't you, class? And in fact, you do. Just add them up. All right. By the way, does anybody not know how to do what I'm doing on the calculator? Anybody at all? I'm not going to, you don't know what kind? What kind?
Oh, TI-84.
A what?
TI-84.
Well, go back there.
Well, he also has a TI-84, and we were putting in the same numbers, in the same mode, and I was getting different answers.
All right, then there's something with you have your calculator set different. I'm going to level with you. Listen, all these calculators, if it's the same model number, unless there's been something changed, you should be able to do, if you look it up on YouTube or Google, and they show the steps, and they have a guy doing it, and you don't get that, you might have a setting in your calculator that is like, instead of degrees, it's radians or something stupid like that. Now that I do know happens.
Well, that's what I'm saying, we checked them the same. Like, they were close. Like, it was earlier, the last question you did, it was for, like, calculating the J of the capacity.
You're close, but I got
it. Was, like, he got, like, 2.002, and I got, like, 2.32.
It's probably something that's in a memory element that's different. Or you could set that thing to a higher or lower resolution, I think, but I don't know how to do that. All right, class, I know about out of time. Are there any other questions? Now hear me. I'm going to give you some more problems. Make sure you do all the problems from the last 2 homeworks for the quiz. And know how to use your calculators. There is no forgiveness for messing up using a calculator on this. That's the whole point of this. They're trivial problems, but you have to know how to use it. Some people, I had one guy say, well, can I use my phone? No, no, you can't call your friends.